An example of uniform circular motion, so we're still in this realm where we're talking about uniform motion, so speed doesn't change and we're definitely traveling in circles. Let's imagine you take a mass on a string and you're just going to twirl it around in a circle, right? It's on some sort of a string, so maybe you're standing here, right, twirling that thing around vertically in a circle. So as this mass is going around and around and around, we're going to sort of think about the forces are on it and why it would change direction. So right now, if there was no string, the mass would just fall straight down, but it can't fall straight down because the force of tension on the string is pulling it towards the center to get it to change its direction. So this is what we were talking about with uniform circular motion. The thing is when we're right here on this end, right, there's some mg pointing down and there's some force of tension pointing to the left. So that mg is going to speed it up, right? The gravity is pulling down, that mass is going to speed up as it falls, not uniform, all right? If I'm over here, then the mass is being pulled down by gravity. As the mass moves up, it's going to be slowed down. So again, it's not going to be uniform circular motion. But at these instances down here, we're going to have a special case where the gravity is pulling directly in opposition or helping with that force of tension, and we're going to end up having a case where there is no speeding up or no slowing down. So for these vertical cases, we can look at those as special cases. So let's look at the case where I've got a mass and it's sort of going around in this circle, and we can look at these two cases, one when it's up and one when it's down here at the bottom, right? Free body diagram. Over here, I've got force tension pulling down, and I also have the weight, the mg, pulling it down. All right. Down here, when I'm at the bottom, force tension is pulling up, and mg is in opposition, pulling it down. So we have these two free body diagrams. The thing about traveling in circles is asking the question, how do we set our coordinate system? The coordinate system in this case, we can't say that up is positive because it's going to end up changing as I move around. So we're going to create what we call a radial tangential coordinate system. So if the thing is going this way, we're going to create a coordinate system that moves with the mass, where the radial is positive in and the tangential is positive, the t is positive in the direction of motion. So what happens is, as the mass moves around and swings down here, the radial is going to be up and the tangential is still going to be in the forward direction. Okay? So this radial tangential coordinate system moves with the mass, and what that means is, in my coordinate system, radial is always positive inward towards the center of the circle, right? And in these free body diagrams, nothing's going on tangentially, so I don't really need to worry about that. If I apply Newton's second law, sum of the forces radially, I get Ft is positive because it's towards the center, and mg is positive towards the center, equals mass times acceleration radial, and here I get sum of the forces radially, Ft, and minus mg equals mass times acceleration radial. And we know in this circular motion, when it's uniform, the radial acceleration is v squared over r, and so we can actually just make that substitution, and we could say the force of tension is equal to v squared over r minus mg, and here we can say the force of tension is equal to v squared over r plus mg. And we can interpret these two results, right? I've got two different results of force tension. When I'm up here on the top, the force tension is this mv squared over r, my centripetal acceleration, minus the weight. And here the force tension is mv squared over r plus the weight. And we have to interpret whether that makes sense. Well, up here, gravity is helping the mass change direction, so the string doesn't have to work as hard. It doesn't have to apply such a big force. Whereas down here, the string has to support the weight of the mass, and it has to get the mass to change its direction. So it has to do both cases. So the lower tension is definitely going to be bigger, right? So notice that we've developed these equations. We went through our process, free body diagram, coordinate system, write our equations of motion. We didn't even have a problem yet. Well, the obvious problem here would be, what is the force of tension at each of these points given some parameters? So let's look at a sort of a typical set of parameters if you were actually swinging a mass around on a string. Maybe it looks like, depending on an average person, this is a radius of 1.5 meters on this string. What's a typical mass maybe you'd want to swing around is maybe 100 grams. Right? And then, I don't know how fast you can swing. You could probably go around, maybe at a velocity of 15 meters per second. Notice that these are all just, sort of made up numbers for a typical situation. And what I can do then is I can put all these values back into my equations and say, what is the actual force of tension that string would be required to provide in order to swing the mass around like that. I do notice that I did say 100 grams, but our normal units that we like, MKS, is kilograms, so this is going to be 0.1 kilograms. So let's just figure out at the top, force of tension equals mv squared over r minus mg. So it's going to be 0.1 15 squared over 1.5 minus 0.1 times 9.8, right? That's just at this point, plug and chug, 0.1 times 15 squared divided by 1.5, plug that into my calculator, minus 0.1 times 9.8, and I'm going to get 14 newtons as my force of tension. If I do that at the bottom, force tension is going to be mv squared over r plus mg. I'm going to end up with all the same numbers, but a plus sign here. So I'm going to end up with, instead of 14, I'm going to end up with 16 newtons. Okay, so there's my two results, 14 newtons at the top, 16 newtons at the bottom, which is an interesting result because maybe I would say, what if I had a string that could support 20 newtons of force? Then as I'm twirling this around, I'm safe. If I had a string that could support 10 newtons of support, as I tried to twirl it around at this speed, then the string would probably break. And if I had somewhere between here, it would break when it was on its way down, or when it was on its way right towards the bottom, because it could break at the bottom but not at the top. So there's an example of applying Newton's laws in the uniform circular motion application.